Let's open in prayer and we'll get started. Heavenly Father, we are down to just 2 classes in here, and Lord, we need your help to make it through this content, and we need your help that not just making it through it, but that we'd understand it and understand it well to our good, to your glory. Help me to teach well and concise and not skip things, not being too big of a rush. Help all of our minds to just really be clear and to remember things that we've already learned and put these pieces together. We pray this in Jesus' name. All right, so last class we talked about ionic bonding, and we talked about covalent bonding, and we talked about electronegativity and how that is really the thing that determines whether it's going to be ionic or covalent. We learned that we've got ionic, and then covalent you've got polar and nonpolar. To be nonpolar, it has to be what, like 0.4 or less in terms of the difference in electronegativities, and then the threshold between going ionic and polar covalent is 1.8. So those were the 2 math things, and you might want to just write that down. 0.4 is the threshold. I can do it like this. So difference in electronegativities, okay? So if it is less than or equal to? No, it's just less than, excuse me. It's less than 0.4, or if it's less than 1.8. Okay, this is our range. Then this is going to be ionic. Over here, anything greater 1.8 or greater. This is going to be truly nonpolar, 0.4 or less, and this one is going to be polar. Now, as true as this is for any one individual bond, I do need to clue you in on something that did not get mentioned. And it didn't get mentioned, not like it was in the content, I skipped it, but for whatever reason the content skipped it, and I think it's worth catching. So I want you to think about a tug of war. That's essentially what we're talking about here. So the electron, the bond, is a tug of war, and if you're more electronegative than me, then it's going to get pulled your way, right? You can imagine that in a rope, whoever has the strongest pull. But what if instead of 2 teams pulling, what if there were 3 or 4 or 5 or 6 teams pulling? So imagine a situation where you got a tug of war, okay, and you got somebody pulling over here, and they're pulling against this guy, and he's only pulling with one hand, by the way. That's what he's doing, and he's also pulling on this one, and this one's getting pulled this one. Well, in some ways it doesn't matter how strong this guy is, as long as he can hold on. What really matters is which one of these guys is stronger. And if these guys are equally strong, then it's getting pulled equally, right? Assuming it's a molecule, the right kind of molecule. There's something like carbon tetrafluoride, okay? CCl4. In carbon tetrafluoride, well, it's not even close. Fluorine is way more electronegative than carbon is. Here's my carbon now, okay? Carbon's getting pulled this way, it's getting pulled this way, it's getting pulled this way, it's getting pulled this way. This is 3D. These are all, I believe, 120 degrees, if I remember all this correctly from way back in the day when I had all this. And fluorine's pulling it this way, and fluorine's pulling it this way, and fluorine's pulling it this way, and fluorine's pulling it this way. Each one of these fluorines has a greater pull than the carbon does, but because it's being pulled equally in all directions by the same level of force, well, there is no charge whatsoever. So something like carbon tetrafluoride is nonpolar. Okay? But then I could do something like, let me do nitrogen trifluoride, okay? In this case, if I were to draw it, it would look like this, right? It's got 2 unbonded electrons up here. If I were to draw this 3D, I've got nitrogen, and it's got some different bonds forming. We're doing it with fluorine, right? Well, this is not pulling all directions. See, there's no pull up here at all, right? So this is pulling down towards each of these, right? That's not a thing, it's just, okay? And because it's being pulled down in 3 directions, very hard and not at all up here, well then, this does have a pull. It's being pulled like in the middle. Think of it like a tripod. And so like the center of the tripod would be the center of like this force pulling straight down, okay? So that would be polar. This one's not polar. As we talk about this, we're only talking about in like one individual bond, okay? I don't know if that's essential for this particular lesson, but it is an essential component of chemistry. It's something that will come up if it doesn't come up shortly. All right, let's go back. I slept funny, and I've got like this crick in my neck, and so I'm like, it's rough going. It's okay. And I'm a year older today.
It's your birthday?
It is.
Oh my gosh, you're lying. My birthday was yesterday.
Is it?
Yeah.
Happy birthday to you.
Happy birthday to you too.
I am 45.
Happy birthday to both of you.
That's right. What'd you get us? Happy birthday. Okay. Okay, so we did this, I think. Okay, let's do this. We had a meeting afterwards, and it took like the whole thing, and I didn't get to print off what I wanted to get printed off for you guys. So here we are, and I wanted to give you this, and you just don't have it. I don't have any time to print it. I'm going to assign a homework assignment. It'll be easy. Go look at it. This is not hard at all. You literally don't need me for this. You need to look at this, but you don't need me for this. You just need this for this. Let's move forward. Lewis dots. These are great, okay? So instead of, when I drew up here and I went, hey, it looks like this. That was in Lewis dot form. It's simplified, but this is Lewis dot form. In Lewis dot structure, you're only going to give the valence electrons, okay? So let's make this real simple. Let's do the first 10 elements, okay? And here's what I want you guys to do. I want you two, since you're the ones here, I want you to come up here. It's going to buy me time while I go make some photocopies of something you need. Come up to the board real quick, okay? This isn't going to be hard. I want you to do the odds and you do the evens. Are you okay doing that? It's going to be on film and all that kind of stuff.
I think so.
And wrong is wrong and who cares? It doesn't matter. This is learning. This isn't like perfection. So you can pick a color, you can use black, you can do whatever you want, but you're going to do the odds, you're going to do the evens for the first 10. I'm going to make some photocopies, we'll reconvene.
Is it just like,
I guess so.
okay, I remember doing this at one point.
I do the odds, you do the evens.
Yeah.
Okay. So I do the hydrogen.
I do.
Yeah, you do the. I'm doing.
You're doing evens.
Okay.
So, you said the first 10?
Yeah.
I remember there's a pattern to it. You're supposed to start somewhere and go around. Are you filling them up? Like,
Yeah,
would this be 2 and then 3?
it's just like the valence electrons. So the first shell has 2. So I guess this just has 2. So like lithium has 1.
Can we do that?
Yeah, and then 3 and then 5.
So would 3 just be like that, or would I just do like?
I think like that. I think like that.
This?
Yeah.
Okay. It's hot up here. Would 4 and just be 1? I'm lost, I'm not gonna lie.
Okay,
I'm
no,
like
it's no problem.
struggling here.
Okay, so here's the deal. If it's in group 1, right, so hydrogen, lithium, sodium, how many valence electrons does it have?
Only one.
1, so it just gets 1, boom, okay? And then if it's in group 2, how many does it have?
2.
2, good. So, and one thing that you guys are showing that's really good, you should think about it. So this is, the first one is my 1s, right? Hydrogen, helium, they just have the 1s, right?
Yeah.
1s. And so they go 1 up and they go 1 down, but they're in the same orbital. So that's good. And then we go 2s, right? And we fill 2s before we go to, or I'm sorry.
Yeah. Yeah.
Go ahead and fill your 2s, and then we go to 2p, and we'll go 1, 2, 3, 1, 2, 2, 2. Okay. The catch is, it doesn't really function like this. They'll hybridize, and so based on what we're drawing here and what you'd expect, what we're going to, and it's true, we are going to fill our 2s before we go to our 2p, in which case you expect your carbon to look like this, right? Carbon doesn't actually do that, because when it's time to bond, this is going to, because of bonding energies, this is going to hybridize and it's going to go like that. So you drew that correctly. So let me do this.
Can we see it?
Yeah, you can see it.
Okay.
No.
Hydrogen is good. Helium is good. Lithium is good. Next up is beryllium. It's looking good. That's fine. And then we'll go boron, which is good, right? And then we'll go carbon. Carbon's looking good. Now anything past carbon, we've got to start doubling up, right? So we go nitrogen. So first thing I do is I do put 1 on each side. Nitrogen has 5 valence, so now I got to double 1 of them. So I'm going to draw it up at the top. Does it actually matter if it's at the top?
No.
No, I could put that in here. Remember, this is in 3D, right? You know, if you ever, I don't want to jade you, if you ever had the fortune or misfortune of taking organic chemistry, one of the things they will teach you is to do this. Go like this.
3 finger rule.
This is your, no. This is your, you're modeling carbon. Here. Organic chemistry. This black one is carbon. Carbon makes 4 bonds. You, with your hands, are doing, you're modeling this. Okay? And so you got a bond coming here, and here, and here, and here. Well, when you're naming and modeling compounds, you'll see kids in there, and it's really crazy. They'll be sitting there going like in their minds, they're seeing other things ticking off, and they're like, it's really bizarre. Because these things can move, they can shift, they can, you know, they're not locked in one position. So same thing here. Okay, nitrogen. Next is oxygen. He drew oxygen with doubles on bottom, doubles on top. That's fine. If he'd have drawn it like this, it would have been fine. Remember, it's 3D. He can move it wherever he wants. Now we come over here to fluorine. How many does fluorine have?
7.
7. So first thing we do is put 1 everywhere, right? And now we start filling in until we get to 7. Good. And next comes neon. Neon has?
10.
Yeah, how many in the valence?
2, but
No, not in the valence.
8.
8 in the valence.
But it's cool.
So it gets 1, 2, 3, 4, 5, 6, 7, 8. And neon's full. Okay? So this is good. We can actually, this is not, you can look at your periodic table and you can figure out exactly how many valence electrons or how many dots to draw for every single one. Okay? Let's do it. Call it a number. Or I'll call it a number.
Okay,
Any number.
28.
28. So I go find atomic number 28, and I see that it's in the D block, right? Okay? So how many valence electrons it can have if it's in the D block? Remember, it fills S's before it fills D's. 2. So anything in that D block will, as a standard, will be drawn with 2 valence electrons. Okay? How about number 16?
16 is in 16.
Atomic number 16 is element
Sulfur.
sulfur. What does it look like?
Like same as
It's
oxygen.
going to look the same as oxygen. So how many is it going to have? How many valence electrons will it have?
6.
It's going to have 6 valence electrons. Good. And take a look at selenium below it, and tellurium, or polonium, or whatever that one below it is. I can't pronounce it. Those are all going to have 6 valence electrons. This is part of the periodicity, right, of the periodic table. Fluorine, chlorine, bromine, iodine, astatine, these are all going to have 7. All your noble gases, excluding helium, are going to have 8. Beryllium, magnesium, calcium, strontium, barium, radium, they're all going to have 2. Hydrogen, lithium, sodium, potassium, rubidium, cesium, francium, they're all going to have 1. Boron, aluminum, gallium, indium, thallium, and that U one, they're all going to have 3, right? So, as a standard, we'll do up to 8. That won't always hold true. There's going to be some weird things that come on, but this is the basic. Okay, so that's how you draw individual atoms, which is super, super important. But this is useful for more than that. This is useful for drawing bonds. Do me a favor and do, let's draw carbon tetrachloride, CCl4, okay? Now, one quick thing I want to remind you of, just because I draw CCl4 doesn't mean that it's carbon bonded to fluorine, bonded to fluorine, bonded to fluorine, right? In other words, it doesn't, I don't have this. I don't go C, Cl, 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 and oh, I've got to bond all these. That doesn't work, actually, right? Because these two would be satisfied at this point, because they each have 7. They only want to make 1 bond. They wouldn't bond to this. I need to do this in such a way that it makes sense for everybody. Each chlorine, oh, actually I need another chlorine, don't I? Each chlorine wants to make 1 bond. How many bonds does carbon want to make? 4. So I'm going to have a central carbon atom with 4 chlorines attached to it, right? We're going to do this 2D. We're going to put a carbon in the middle. How many electrons are on carbon? 4. So I go 1, 2, 3, 4. And now I need to do chlorines. Right angles here will help. Each chlorine has how many electrons? 7. Look at where they're at on the periodic table. Right, next to noble gas, they're going to have 7. I'll just give you a hint. It'll help if you draw your 1, your unshared electron near carbon. It's just going to make this smoother coming up. If you don't, it's okay. We can just erase and move electrons. Then you fill in your others. So 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So at this point we should look like this. When you get a chance, go ahead and just peek your eyes up at it. And now we just do connect the dots, right? You will occasionally, I'll give you a second. We'll occasionally see this done different ways. You may sometimes see these as like people just draw lines for pairs of electrons because that's easier for them. Nothing wrong with that. You may see people circle them. They may circle all of them. Okay, I don't think that's easier, but whatever. Once you really get blowing and going, what you're pretty much going to see is a skeleton structure. These are all representing the same thing. For right now, let's do dots and connect the dots. That's going to be the simplest for us. And that's where we need them. So, okay, why don't you do boron tetrahydride. Or no, boron trihydride. I said the wrong way. So BH3. Boron atomic number?
5.
5. How many in the first? 2. How many in the second? 3.
Does it really matter which way you kind of,
Spatially?
yeah?
Nope. What kind of monster doesn't draw this way? But we do water. Do H2O. Do H2O2. Or I can draw this a whole bunch of different ways. It doesn't have to be drawn this way. There you go. I could draw like that. I could flip these. Like these things, if we were dealing with molecular model kits, I mean, the parts move. So you just got to know that these are all saying the same thing. Okay, they're equivalent. All right. We draw something different. Let's do, what do we want to do? Let's do some organic chemistry. Let's do C2H6, C2H4, and C2H2. Do each of those. While you're doing that, I'm going to go grab what I printed. So C2H6, and now I'm going to have a bond between my carbons in each one of these. Here I got to pair it with 6 hydrogens, right? I have 1, 2, 3, 4, 5, 6 available electrons. So these are all going to be single bonds everywhere that I go. So this is exactly what we already know how to do. This is no problem at all. Here I only want to pair it with 4. So I'm going to go ahead and I'm going to pair it with 4. Here, I only want to pair it with 2. So I'm going to pair it with 2. Now, every unbonded electron must bond with itself. I've got an unbonded electron here and one here, so it has to bond. I've got one here and here, and I've got one here and here, so they have to bond. So this one has a C2H6 has a single bond, C2H4 has a double bond, C2H2 has a triple bond, right? I just handed you a little printout from the book. Has some stuff on double and triple bonds. It says, as previously mentioned, when a pair of atoms shares one pair of electrons, we call this a single bond. However, a pair of atoms may need to share more than one pair of electrons in order to achieve the requisite octet. A double bond forms when 2 pairs of electrons are shared between a pair of atoms. That's between carbon and oxygen atoms in CH2O, which is formaldehyde, or between in ethylene, which we just drew. A triple bond forms when 3 electron pairs are shared by a pair of atoms, as in carbon monoxide and the cyanide ion. Okay, I wish I hadn't given you this. I'd make you draw those. They're fun. All right, let's do carbon monoxide for a second because it's fun. It's worth taking a look at. carbon monoxide. Carbon gets 4, right? And oxygen gets 6. Okay. So, you know there's going to be one bond, right? No problem. But nobody's satisfied, so I need to go ahead and I need to have another bond, right? Right? Now, it's weird because oxygen is satisfied, right? 1, 2, 3, 4, 5, 6, 7, 8. But carbon is not. Carbon needs 2 more electrons. Okay? Let's take a look at it. Make sure you see this. Oxygen fully satisfied, carbon not. Carbon needs 2 more electrons. The only one he has to get them from is oxygen, right? That's it. So here's, what can I do?
They share the electrons.
Yeah, they can share another set of electrons, right? So that makes a triple bond. Now let's see, how many does oxygen have? He has 1, 2, 3, 4, 5, 6, 7, 8, 9. And this guy has 1, 2, 3, 4, 5, 6, 7. We're in balance. So I can't, just bonding again is not going to solve this problem. It's only going to make it worse for oxygen. Instead, what I need to do in a way is to like give that electron over there. Okay? So this is a unique situation. If I were to redraw this, what happens in a situation like this is oxygen doesn't give his electron necessarily so much. It's not like it swaps and runs over there. What does happen is we get this triple bond. Oxygen has this unshared pair, and this last bond is a special kind of bond. I'll deal with that in a second. So here's oxygen, right? What happens for carbon is instead of sharing this way, this electron is going to these two are going to fill the same orbital, okay? And now oxygen is just basically freely going to share both of these across this, okay? So this is just a standard double bond. This is the part that I'm trying to get you to get right here. This is what we call a coordinate covalent bond. Now, in a coordinate covalent bond, both electrons in the bond come from the same atom. They're given from the same atom. Carbon is not contributing anything to this coordinate covalent bond. It's only receiving. Oxygen is giving both. So in coordinate covalent bond, one atom donates both electrons in the bond. Okay. Make sense? This is not the only coordinate covalent bond that we will encounter. This happens not all the time, but it happens often enough. We had the case earlier of drawing boron, right? Boron has 3 valence electrons. And then we drew ammonia. I'll draw ammonia again. It's got a free pair of electrons. He's got none. For him to satisfy, and he wants to satisfy that octet rule so bad he can taste it, right? So if these two come close enough, get that. He contributed nothing to this bond, right? This is a coordinate covalent bond, right? All right. So all that because I decided to go talk about carbon monoxide, which you didn't even necessarily have to do, but here we are. We learned about a coordinate covalent bond. You're going to learn it anyways, if not today, the next time. All right. Where were we? Triple bonds. Good. Writing Lewis structures with the octet rule. So they're giving you just some rules for how to do this. It says for very simple molecules and molecular ions, we can write Lewis structures by merely pairing up the unpaired electrons on the same constituent atoms. See these examples. So hydrogen and bromine, 2 hydrogens and sulfur, nitrogen and nitrogen. Let's do nitrogen and nitrogen, okay? So this is diatomic nitrogen gas, N2. I guess it's liquid if you get it cold enough. I don't know how cold you'd have to get it to solid, my goodness. But if you were to draw nitrogen, right? And then another nitrogen. This should be fairly easy. All I have to do is put them near and pair unpaired ones, right? So we just go 1, 2, 3, and you can see that this has a triple bond. Okay. Number 2, draw a skeleton structure of the molecule or ion, arranging the. Oh, well, I'm sorry. Then it's giving us a rule. It says for more complicated molecules and molecular ions, it's helpful to follow the step-by-step procedures outlined here. So it's giving us some steps to do. Number 1, determine the total number of valence or outer electrons. For cations, in other words positively charged ions, subtract 1 electron for each positive charge. For anions, add 1 electron for each negative charge. Then draw a skeleton structure of the molecular ion, arranging the atoms around a central atom. Generally, the least electronegative element should be placed in the center. Do you remember where I'll find my least electronegative element? Of all of them. Bottom left. My most electronegative? Top right, right? It's going to be fluorine, and we ignore the noble gases. Distribute the remaining electrons as lone pairs on the terminal atoms except for hydrogen, completing an octet around each atom. Number 4, place all remaining electrons on the central atom. Number 4, rearrange the electrons of the outer atoms to make multiple bonds with the central atom in order to obtain octets wherever possible. Great. We said all that. What does that actually mean for us? I think we need to practice one. Do not turn your page, okay? Let's do HCN. Let's practice that one. HCN. Okay, so we're going to follow our rules for this, okay? So rule number 1 is to determine the total number of valence electrons. So how many does hydrogen have?
1.
Carbon?
4,
Nitrogen?
5.
5. So we're going to have a total of 5. Or 8, I'm sorry. Or 10. Whatever I need to say. Then draw a skeleton structure of the molecular ion. Arrange the atoms around a central atom. Generally, the least electronegative element should be placed in the center. Okay, so we're going to go carbon, and now we're going to go nitrogen, and we're going to go hydrogen. Okay. Then connect each one with 1 bond, it says. Okay. Then number 3, distribute the remaining electrons as lone pairs on the terminal atoms except for hydrogen. Okay. Connect, what now? Connect each atom to the center. Distribute the remaining electrons as lone pairs on the terminal atoms. So that would be like this. Is that what it's telling me to do? That looks funky to me, but okay. We'll follow it. We'll see how it goes. Distribute the remaining electrons slow in pairs on the terminal atom, except having completing an octet around each atom. Okay. That would work for nitrogen, right? Now place all remaining electrons on the central atom. We have none left, do we? Because we wanted 10. I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now rearrange the electrons of the outer atoms to make multiple bonds of the central atom in order to obtain octets wherever possible. So it's telling me to do that, and it's telling me to do that. All right, that worked. That worked. Should we try it again? Let's do the same thing for H3, C, CH3. H3, C, CH3. This won't be hard, I don't think, right? This is
Yeah, we
easy.
did it already.
Huh?
We did C2.
Yeah, we're going to skip this. Let's do, where's some of the other ones it gives us? We already did ammonia. These are not hard. These are too easy. Let's do, do carbon dioxide. Let's start with that one. Do carbon dioxide. So follow these rules, right? My least electronegative is carbon, so it goes in the center. I draw a single bond to each one. And now I put pairs of electrons around everything else. Oh, I skipped a step. Carbon has how many?
4,
4. Oxygen has
6.
6, but I have 2 of them, so it's 12. So I need 16 electrons, right? Okay. So I've got 2, 4, 6, 8, 10, 12, 14, 16. Okay. And now it says to move them in such a way that I can fill in what's lacking for carbon. I have none left to give to carbon, but what I can do is I can go, hey, I'm going to move this one over to here, create a double bond, and I can move this one over to here, and then create a double bond, right? Of course, if I want to clean that up, I'd go like this. Okay, that works for me. It's just firing over there. Let's do that one. What does carbon have?
4,
4. Oxygen?
6,
6, 6, and
1.
1, and I have
Maybe.
1 extra, right?
Mhm.
So there's 1. So my total is 10, 16, 17, 18. 18 electrons. Okay? All right. Let's hope I didn't mess this up. So I've got oxygen over here. It says to fill these out, right? So 1, 2, 3, 4, 5, 6. So right now I've got 6, 7, 8, 9, 10, 11, 12. Now I can start filling in on my interior, right? 11, 12, 13, 14, 15, 16, 17, 18. And look at that, that would work. Sometimes my freestyle, I don't know how it's going to go. Sounds like, oh, let's do soda. All right, you know, you've been here long enough. All right. These are too easy. You guys are way smarter than this. Do you want me to freestyle one more, or should we move on? It's your call. No? All right, you're over it. Okay. Let's do this. Exceptions to the octet rule. Okay. Many covalent molecules have central atoms that do not have 8 electrons in their Lewis structures. These molecules fall into 3 categories. Odd electron molecules have an odd number of valence electrons and therefore have an unpaired electrons. Electron deficient molecules have a central atom that has fewer electrons than needed for a noble gas configuration. And hypervalent molecules have a central atom that has more electrons than are needed for a noble gas. So, 3 exceptions to the octet rule. Okay. So number 1 is going to be odd electron molecules. This is going to be odd number of electrons, okay? Let's work with this one first. Okay. We call molecules that contain an odd number of electrons free radicals. Have you heard of that term before?
Yeah.
Okay. Free radicals are very dangerous.
You can bond. Because it can bond, is that one like?
Yeah, not just can, like it's itching to. And it can tear apart cells, it can tear apart DNA. Can cause, it can cause changes to DNA that can cause cancer and things like that. I mean, these are just dangerous. And so one of them is NO, nitrous oxide. Okay, nitrous oxide is produced by cars. Okay, let's do it. We're going to try to follow the same rules. It says here, determine the total number of valence electrons. So how many does it have? How many does nitrogen normally have? 5. How many does oxygen have?
6.
6. Okay. So we're going to have a problem. Now, if this were an ion, that'd be one thing, right? But this is not an ion. Okay. So we're looking for 11. Okay. Draw this, we're going to draw that structural skeleton, right? So I need to do N, O, right? What's my more electronegative atom? Oxygen or nitrogen?
Oxygen.
Oxygen is, so I begin putting my dots. 2, 3, 4, 5, 6, 7, 8. How many do I have total? I have 11. 8, 9, 10, 11. And now I will shift electrons to get nitrogen as close to an octet as I can. So I'll move one of these over here, right? And I'll give this a double bond. Now oxygen still has 1, 2, 3, 4, 5, 6, 7, 8. He's satisfied. This guy has 1, 2, 3, 4, 5, 6, 7. He's close. He's a free radical, which means that this is the. Technically, I guess it'd be better if we drew it like this, right? But this is what this looks like. And because it has this 1 and it's just itching to get 1, it's going to bond with things. It's going to be a problem. Okay. Should we do any others while we're at this? Really good similars. Okay. Let's go do electron deficient molecules. That's our second. So we did the odd electron molecule, the free radicals. Now we're going to do electron deficient. That's our second example. Hope you didn't write that too close if you did it, because I messed you up. Electron deficient. I'll give you right now that number 3 is going to be hypervalent. What time do we have?
126.
Hey, I'm doing pretty good. Electron deficient and then hypervalent. So, okay. Electron deficient molecules. Yeah, we've been dealing with boron. It's like, yeah, you can just bond with what you got, and that's all you got. That's literally like all this is saying. So let's just do a couple of these. Why don't you do beryllium, difluoride. Let's do boron, trichloride. I don't know. Let's do aluminum. That'll be fun. That'll be a little more challenging. Let's do that. And shoot, let's do gallium. What can I make you do with gallium? There's only so much you can do with this. Ooh, I can challenge you. That's a good one. Do those. That'll be fun. Still want you to treat it the same way, right? So you can go BeF2. Oh, beryllium has how many valence? 2. Fluorine has? 7. 7. And I have 2 of them, so 14, right? So I want 16. Okay. So I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. That one's done. That's easy. Oh, this should be BCl3. I'm sorry. I do apologize. BCl3. Boron trichloride, right? How many valence electrons does boron have?
3.
That's 3. How many does chlorine have? 7. BCl3. So this is 3, and then 7 times 3 is 21. So that's going to be 24. So I go boron, and then I got to get it to 3 chlorines. He only has 3. Here I go 1, 2, 3, 4, 5, 6. 2, 3, 4, 5, 6. 2, 3, 4, 5, 6. Well, it's 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Okay, good. That's easy. AlHO. Okay? So my central atom is going to be probably aluminum, right? Because that's what I'm dealing with. Aluminum has how many valence electrons? 3. Okay. So what am I bonding in with? Hydrogen, and oxygen. Okay. Good. So aluminum has 3, hydrogen has 1, oxygen has 6, so that's 10, right? Okay, so right now I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, good. He's satisfied, he's got his 2, he sees 4, right? He'd like to see 8. So based on my rules, I could do this, couldn't I? That's kind of cool. Does that work out? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Everybody's happy. Good. All right, let's do this one. I am taking you guys into like weird territory, right? Gallium, how many valence electrons? 3. Who's he bonded with?
Hydrogen.
Hydrogen.
And nitrogen.
Yeah. Nitrogen has how many valence electrons?
Nitrogen has 5.
5. Let's do F3. Each of these has 7, so that's 21. And that's 5, so that's equals 26. So I go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. Right? Now, in reality, this was not fair for me to give you this. Right? This is crazy complicated. This guy's done, and yet I put them together. That's because I did introduce you earlier to the coordinate covalent bond, and so we'll go like this. And that's how that would work. Okay? That'd be desperately mean, but don't think I wouldn't do it. All right. Well, the good thing to know is, if your book doesn't do it, I won't do it, because I'm going to take practice problems and just rework it, right? So if your book stays away from this at this stage, then you'll be safe. If it has it, then you're in for it. Because I like these, because this would be the hardest one you get, is something like that. All right. And the last one is hypervalent. So this is where it gets just interesting in a very different way. So elements in the second period of the periodic table, n equals 2, can accommodate only, so the second line, right? So the first line, n equals 1, we have hydrogen, we have helium. The second one, n equals 2, we've got lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. That's n equals 2. They can only have up to 6, right? Because they hold 2 in the first, and then, I'm sorry, up to 8. 2 in the first, 8 in the second. But then, when you start getting up to the next one, it gets more interesting. We got all kinds of these other electrons that we can deal with in our D block, right? So that's what's going on here. It says elements in the second period of the table can only accommodate only 8 electrons in their valence shell orbitals, because they only have 4 valence orbitals. Elements in the third and higher have more than 4 valence orbitals and can share more than 4 pairs of electrons with other atoms, because they have empty d orbitals in the same shell. Molecules formed from these elements are sometimes called hypervalent molecules. So let's do some. Let's do PCl5. So look for where phosphorus is at on your periodic table. Phosphorus is right below nitrogen, so how many how many does it normally have in its valence shell?
5.
5. Okay. So normally you go 1, 2, 3, 4, 5, something like this, right? And we go, okay, well these two are paired, so he's only going to make 3 bonds. And that would be true of nitrogen. But this guy, because he has a d block, can actually kick an electron out of here and into one of the d orbitals. And so instead of dealing with just 4 orbitals to work with, 4 dimensions, we can deal with 5. Okay? And so on this, what we do is we go, when it doesn't work the way it should, so we would expect PCl3 and that would be completely valid. We're saying PCl5. So what I got to do is I have to treat this very differently. I'm going to look at it the same for right now, okay? I'm going to put a Cl off of each of these. Okay? Now, oh, sorry, I got to go ahead and bond these, don't I? But now I've got to put 2 more off here. So I'm going to go here and here. Chlorines are all fine, they're meeting an octet rule. But this guy's seeing 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's only possible because he has those d suborbitals that you can go into. So that's how you'd handle that. And then another example, let's do sulfur hexafluoride. So SF6. Okay, I'm not going to do this one. I want you guys to do this one. I mean, I'll do it in a minute, but I want you to have a run at it without me first. So you should have this giant mess, right? And so each one of these fluorines wants to make 1 bond. You should have something like that, yeah. Life's good, 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 good. I'm doing great. Let's see. Let's do IF5. Iodine pentafluoride. Do that. How many valence does iodine have?
7.
7. And fluorine?
7.
7. We start off with something like that, right? Okay. Now I only want 5 fluorines. Well, the first thing I'm going to do is bond with this unbonded, because that just only makes sense. Why create problems I don't need to have? So that one's good. Now I need 4 more bonded, so I can pick any of these I want, but what I don't want to do is this. I don't want to go like 1 here, 1 here, 1 here, 1 here, and then leave these guys.
You want to leave a pair?
Because I have 3 in this orbital, right? That doesn't work. So I want to leave, basically I want to leave 1 orbital filled, unbonded, and I want to take the other and kick it out here, okay? Let's do one more example of this. Let's do xenon tetrafluoride. How many valence electrons does xenon have?
8.
8. How many bonds does it want to make?
None.
None. This requires a lot of energy to make happen, right? And very special circumstances. So I draw my xenon. Okay. Now I need to remember, I don't want to go splitting up pairs if I don't have to. So I only need to make 4 of these. So I'm going to go something like this. Okay. That ought to get it done. Okay. All right. I want you to do xenon difluoride and xenon hexafluoride as sample problems. So XeF2 and XeF6. Go ahead and do those. How you feeling?
I think I got it.
I think you do too, but I just want. Yeah, that's great. Perfect. So there's item The only ones here that are complicated at all are the ones that are coordinate command. Okay? Those will be just recognizing, hey, something here doesn't quite add up. How do I figure this out? Possibly even just dealing with ones that have charge, remembering that that's what's going to, I've got to account for that. Oh, I've got to take an electron away. I've got to add an electron in. That's what's going to balance this. I'm not going to be there for your test. To where you can walk up to me and go, hey, what's going on here? I'm having trouble with this one, and I can go, oh, don't forget your charge. I'm not going to be there. So you've got to remember that on your own to look for charge on an ion. Okay, pay attention to that when that comes up. Okay. All right. Otherwise, I think that was great. We got one more lesson for the semester. Hope you take next semester. Hope I'm not teaching to thin air. Totally awkward. But yeah, I'll say goodbye next class.
Hopefully everyone shows